Hi everyone, my name is Johann. I'm a grad in the Graduate 2022 program. And today I'll be talking to you guys about a project that I've been working on, a IoT UPS switchover device that I'm currently building. So just a quick overview of what we will be talking about today. I'm going to be introducing the problem, to give a bit of background there, what my solution is to that problem, as well as the tech I use to solve this problem, how it all works, and then I'll conclude with some future ideas and improvements I still want to render on this system. So what is the problem? At home currently, I have a UPS running on some batteries connected only to solar panels. To this UPS, I've connected multiple devices, including some fridges. The idea here is that we want to run all of these devices from solar power, saving a bit on electricity costs. However, our battery capacity is not enough to work 24/7. Therefore, during nights and sometimes on rainy days, we have to start prioritizing which devices to run on the UPS. So we physically have to disconnect these devices, either leave them unplugged or plug them back into grid power. Now, this is all a lot of effort, as you can imagine. And even more problematic, sometimes when we forget to do this, let's say during night, we actually run into a situation where the batteries run flat in the middle of the night, causing the UPS to crash, alarms, everything. Very annoying. The solution to this problem, simply let a robot do all of the work for you. Additionally, instead of unplugging the devices, we want to rather charge the batteries, but we don't want this charger to run 24/7. We instead want to only charge when we need to, for example, during nights. This will still let us save electricity costs. More specifically, we need a system that can accurately measure battery voltage, keep track of time, switch devices on and off based on some predefined rules that the user can define, and also switch a battery charger on and off. So the tech I used for this system, I decided to go with a Wi-Fi capable microcontroller, namely the ESP32. Coupled with that, I have a SD card module we used for permanent storage of all of the assets and stuff that I need. And then I also have a relay board that connects to this ESP. To program the ESP, I used platform.io. And for those of you who are familiar, that's very similar to Arduino. It has a lot of stuff in common with Arduino, but it offers better code completion, integration with Visual Studio Code, and also it has faster compilation times. Usually with Arduino, something like this would take 2 to 5 minutes to compile every time you make one small code change. Paired with that, I have a Angular front end that I built that is hosted on the file storage or hosted through the ESP. And yeah, that's used to interface with the actual system. So let's look at the project from a hardware architecture perspective. So in the middle, we have the ESP32, which is the heart of the project. On the right-hand side, we have the micro SD card module that interfaces with it through the SPI bus. The micro SD card module is where we would host the Angular web files, as well as the engine configurations and the user-defined rules. At the bottom, we have the relay board, which is used to connect all of the output devices to the UPS, either switching them on and off based on the signals coming from the ESP32 over the general purpose input-output. On the left, we have the UPS, which is connected to the UPS battery. Now, the UPS battery are two 12-volt gel batteries, making up a nominal voltage of 24 volts. So the voltage there can range between 23 and 27.5 volts. So the buck, we connect the ESP32 directly to the USB battery through two devices. First, the buck converter, which is used to buck down the voltage to a stable 3.3 volt, used to power the ESP32. We then also have a voltage divider circuit, which scales down the voltage between a range of 0 to 3.3 volts. This is then used by the ESP32 to actually measure the voltage of the UPS battery without damaging the ESP. From a software architecture perspective, we once again have the ESP32 as the primary component. On the left-hand side, we have an Angular single-page application that is both hosted by the ESP32 and connects back to the ESP32 through the REST and HTTP protocols. So the ESP32 exposes an API. Internally, we also keep track of time, but due to crystal oscillators not being 100% accurate, time will drift over time. And we therefore have to sync time. We do that by connecting to the global NTP servers through the UDP and NTP protocols. And then we once again have the SD card flash storage that connects to the ESP through hardware SPI. Let's take a look at the algorithm used to control these devices. So the algorithm consists of a set of user-defined rules that can be modified on the Angular front end. The algorithm will then run through all of these rules and evaluate them in the order that the user specified. This allows us to cascade the rules and provide overrides. So once a rule has been determined to change an output device, we only update the virtual state of that device. Once all of the rules have been evaluated, we compare the virtual state to the physical state. But then before actually updating the relay, switching it on and off, we actually first check if we haven't already updated the physical state within a certain period of time. I here said once per second. This is to ensure that we don't switch these relays on and off too fast because they have a limited lifespan. Because this Arduino, sorry, this ESP can run, this algorithm can run potentially thousands of times per second. So what is a rule? A rule consists of three components: a time range, which is used to determine when this rule will take in effect. For example, we only want to turn on the charger from 4 o'clock in the afternoon until, let's say, 8 o'clock in the morning. Anything outside of that time range, the rule will immediately be skipped. We then have an on and off voltage. So the on voltage, so if the battery voltage is currently above the on voltage, the device will be switched on. If it is below the off voltage, the device will be switched off. There is a rule that flips this if the on voltage defined is above the off voltage. This is used in the case of the charger. Now, the reason why the on and off voltage are different voltages is because we don't want to run into a situation where the voltage floats above and below the threshold, switching the device on and off very rapidly. For example, let's say the threshold was 24 volt. We don't want it switching off at 23.9 and switching on at 24.1. So we usually define a set between 23 and 24 volts. And then the last component of a rule is the list of devices to act on. Because a device could, because rules could potentially have multiple devices, because the device, sorry, the rules are shared, we want to define all of the devices that the rule will act on. And this then brings us to future ideas and improvements. I still want to render on the system. I want to implement the load shedding. I want to connect to the load shedding schedule API and get real-time data about when load shedding will happen. That way I can write smarter rules that, for example, I don't want the batteries to run flat just before load shedding starts. I want to start charging them so I have power during load shedding. I want to implement logs and graphs so I can see what my devices are doing, let's say during night when I don't have time to watch them, so I can better implement rules. And then I want to implement a push notification system that will notify you if something goes wrong, maybe if a wiring is missing or that the UPS battery has fallen flat or something.